So today we will speak about Wiener version of uncertainty, which the general meta statement is that function and Fourier transform cannot decay fast at infinity simultaneously. And probably the most impressive and likely it was the first beautiful realization of this principle is a theorem of Hardy, which says the following, that suppose that our function grows not faster than this Gaussian, and Fourier transform grows not faster than the same Gaussian, where in dimension 1. Then the function is Gaussian. And because of our normalization of Fourier transform is the same Gaussian. There is a formal extension. I will mention it. It's easy to check. Which says the following, that suppose that f of x is O capital of e to the power minus ax squared, and f hat of x psi is O capital of e to the power minus b psi squared. Then we have three cases. If AB is bigger than pi squared, then f is 0. If AB equals pi squared, then f is our Gaussian. And AB times b is less than pi squared, then the space is infinitely dimensional space. So first two statements follow from what I will prove just by rescaling. If you rescale f, then you have to rescale psi in the opposite direction, and product remains constant of a and b. If a times b less than pi squared, then it's an exercise. Well, you need to know what are Hermite polynomials or Hermite functions, but all Hermite polynomials times e to the power corresponding Gaussian will satisfy this assumption. So this is a simple exercise, and I suggest to do it. But what we will use today, we will use some complex analysis. And more precisely, we will use one version of maximum principle, which is very important factor. Also in PDE, which is called Fragment-Lindelöf principle. So we will start our lecture with a piece of complex analysis.
Sorry, could I ask the question about what are you trying to erase?
Yes, please.
In the case AB is exactly p squared, do we need that the Gaussian is only with the coefficient pi before the x squared, or it could be coefficient a and then...
Roman, you're absolutely right. So it would be pi over c and pi times c with any positive c. You're
Okay, thanks.
You're right. In the second case, it's rescaled e to the power minus pi x squared. Thank you.
Okay, thank you.
Yeah. I will not write it again. It's I suppose it's clear what we said. So warm up for some of you even heard this from me a few years ago. Let's do the following. This is the simplest version of Ragnar-Lindelöf principle that suppose that we have a function f which is analytic or holomorphic in a half plane. And suppose that f is continuous in the closed half plane and bounded. And suppose that absolute value of f is less or equal than 1 on the boundary. Then absolute value of f is less or equal than 1. So you may think that our half plane is an upper half plane. And certainly you need a priori boundedness assumption. So if you have a function e to the power minus iz, this function is analytic in the whole plane, is bounded by 1 on the real axis, but it grows exponentially with y, with imaginary function. So we need a priori boundedness assumption. The proof is simple, but it takes one needs a nice idea, which we will use all the time in the proof of Hardy's theorem. Let's fix some small positive epsilon and introduce another function f of z over 1 plus z to the power epsilon. 1 plus z to the power epsilon in the upper half plane, in the closed upper half plane, it's nice analytic function. So this function is analytic. Now we fix z in the upper half plane, take very large R, which is bigger than absolute value of z, denoted by PR. Maybe I will make a drawing. PR is intersection of our half plane with disk of radius r. Then the function f epsilon is less or equal than 1 on the boundary of PR. Well, because on this part of the boundary it was less or equal than 1. On the other part of the boundary it was less or equal than some large constant. But if R is sufficiently large, then the denominator will kill this constant. So on the half circle, function can be done as small as we wish. So by the maximum principle, f epsilon is less or equal than 1 PR. So in particular, f epsilon of z is less or equal than 1, then this means that f of z is less or equal than 1 over absolute value of 1 plus z to the power epsilon. And what remains, since epsilon was as small as we wish, we can let epsilon go into 0, and we will get what we wanted to show. But here is an important thing in this trick. So there are two ingredients. One ingredient was to consider auxiliary function to kill a priori growth, to kill a priori big bound. And another, that for the order of the parameters, we are not proving this simultaneously at all points on the half plane. We fix a point z, and then we choose r depending on epsilon. We prove this inequality separately on each point. So this is the simplest version of Fragment-Lindelöf principle, and we will use this more advanced versions today all the time. So now let me come to something more advanced. Will you allow me to erase what today I will ask you all the time, will you allow me to erase what I wrote?
Yeah.
Okay. Okay. So the next version will be similar. I will call it already theorem. Fragment-Lindelöf. Both your Swedish mathematicians. No, Lindelöf was Finnish and Fragment was Swedish in the beginning of 20th century. And suppose that we have a sector or angle of opening less than pi. F is a function holomorphic in the sector and continues in the closed sector. And now our a priori bound will be f of z is less than a, its exponential growth. Suppose, and then the same, suppose that absolute value of f is less or equal than 1 on the boundary, then absolute value of f is less or equal to 1 is equals. We can assume that our sector is symmetric. This is our sector S. Alpha is less. Let me call it alpha, and alpha is less than power of 2. I'm starting to prove it. So we will play the same game. So now we need to kill a priori exponential growth. So our auxiliary function will be f epsilon of z, which is f of z times e to the power minus epsilon z to the power c. And here epsilon will be bigger than 0 and small. C will be fixed bigger than 1, but still alpha C should be less than pi over 2. And what I claim, this function is certainly in this sector S is analytic. So what I claim that we will kill a priori growth of our function. So let's see it. The absolute value of f epsilon of c, absolute value of f of c times e to the power minus epsilon, real part of z to the power c. So let me write that z is r e I theta. A e to the power e absolute value of z. This is a priori bound minus epsilon r dr minus epsilon r to the power c. C is bigger than 1. It's big. Cosine c theta. Well, cosine is positive on this part of the boundary because alpha c is still less than pi over 2. And if c is bigger than 1, so if we choose r sufficiently large, then the second term will kill the first one. So it is less or equal than 1 if r is sufficiently large. On the boundary, still absolute value of f of epsilon of z will be less or equal than 1, because we multiplied by something which is this exponent is always this expression is always positive, so we can only decrease absolute value of f on the boundary. So we conclude again by maximum principle that f of z is less or equal than e to the power epsilon absolute value of z to the power c cosine c theta. Well, and then letting epsilon go up to 0, we conclude that f is less or equal to 0. So this is the proof. We will use this idea more and more often. So here we used just one auxiliary function. So sometimes we will have to repeat this trick several times. But before we proceed, I will mention a formal extension. That we could assume instead of saying that we have a priori exponential bound, we could assume only this. The only thing which we needed is that rho is less than pi over alpha. If here we have r to the power rho is less than pi over alpha, then still on the boundary we will have this bound. So I don't need to assume exponential bound. We could assume this we can a priori bound. So that's all with preliminaries. And I can start proving Hardy's theorem. Can I erase the proof of Fragment-Lindelöf theorem? Oh, well, I will.
Yes.
Yes, probably.
Erase. Proof.
Sorry, a little question. In this formal extension, alpha is the opening of the whole sector, right?
Yes, yes, yes. Alpha is before. Sorry, I think before it was two alphas. Thank you. Yes, thank you, because in my previous notation it was 12.
Thanks.
But this is the same, this is the same. Or you can, there are several options, so you can just make a change of variable and we'll get the previous statement, or you will prove it another time, the second time. It's up to you. So first of all, we have implicit constants here and here. So it will be convenient for me to assume that they are one. So we assume, I will write it here because I have lack of space. So our function f decays super exponentially fast. So our first observation is that f hat is analytic in the whole plane, its entire function. Also f is entire function. So this is an exercise. This is an exercise which was in the first homework. It's not complicated. So if you have a function, say in A2, and Fourier transform decays exponentially fast, then and function decays exponentially fast, then Fourier transform will be analytic in S2. And this is usually, this is like in the analysis course that since we deal with improper integrals, so first we split integral into two parts. When we integrate over finite interval, you check by hand that the function is entire, and then because of a priori bound, you can make tails as small as you wish. So you get a sequence of analytic functions which uniformly converge to something, and the limiting function is analytic as well. So our function is entire, and we can use the same integral formula for it. And
Excuse me, entire function, it is analytic function, yes?
Entire function means this is analytic in the whole.
Oh, thank you.
So my next claim was that, again, because of the same convergence, this integral converge to our functions. So we can use it for estimates. So this is e to the power minus pi x squared. This was the bound for f plus 2 pi eta x dx. No, we put full square as usual. This integral is 1. And now we introduce auxiliary function f of zeta. Zeta is our complex variable, which is e to the power pi zeta squared times f. What do we know about our new function? First of all, if zeta is real, then here we will have e to the power pi psi squared. F hat is less or equal than e to the power minus pi squared. So on the real axis, f is less or equal than 1. This is our assumption. On us already. The second thing which we know that the same holds on imaginary axis. Well, because on imaginary axis, again, due to our assumption, this is less or equal than e to the power pi eta square. And this guy, our factor is e to the power minus pi eta square, and we will get 1. And what is our a priori bound in the whole complex plane? So our a priori bound, if I'm writing here, do you see what I'm writing?
Yes.
Yes.
Thank you. So our a priori bound is e to the power absolute value of our factor is e to the power pi real part zeta square. So real part zeta square is e to the power pi psi square minus eta square times f of zeta. F hat of zeta, sorry. For f hat of zeta, I have e to the power pi eta square, so it's less or equal than e to the power pi. So we have a function analytic in the whole complex plane. It is bounded by 1 on the real axis and on the imaginary axis. And it has this a priori bound in the whole complex plane. And now using, it's not exactly Fragment-Lindelöf which we used, because here, look, we have angles of opening pi over 2, and our rho is 2. So we are in the critical case. We cannot apply directly this formal extension. We need to work a little bit to do it. But the idea is to use fragment-Lindelöf principle, and this is a beauty of this theorem. And I will not use anything only these three properties. I will show that F capital is bounded. Then if F capital is bounded by Liouville's theorem, it is a constant function. If it is a constant function, F hat is exponent, so F is exponent as well. And what we want to show that.
Sorry, could you please repeat why F is less than 1 on the real numbers?
Yes, sure. Look, on the real, when zeta is real, F hat is less or equal than e to the power. Okay, let me do this for you.
Yeah, okay, now I see, thanks.
So I will show only that, so we want to check that absolute value of F is less or equal than 1 in C. Then by Liouville's theorem, F equals constant is a constant function, and we are done with this. So I will check this. We have a symmetry. So I claim that F is less or equal than 1 in the first quadrant. Because we have a completely symmetric situation, certainly. So. Well, we need to play similar games. So we fix beta, which is positive and less than pi over 2. We consider the sector. Opening of the sector is less than pi over 2, so we can apply already fragment-Lindelöf, but we need to fix another parameter. So this is a two-parametric game. And we need to introduce one more auxiliary function. So we consider the function e to the power I delta zeta squared times f of zeta. And let me estimate. This is still function which is analytic in the whole complex plane. Let us see what kind of estimates we will have. I want to apply fragment-Lindelöf principle in this sector as beta, which is permissible, because in this case, rho is 2 and rho times beta is less than pi. Beta is less than pi. So first, let us look at this part of the boundary. So our function f is less or equal than e to the power pi xi squared. Here I use this a priori bound. And absolute value of this exponent is real part of this guy. This is minus imaginary part of delta times imaginary part of zeta square. So it's minus 2 delta psi times theta. This is imaginary part of zeta square. Well, and now look, if beta is close to pi over 2, depending on delta, we will make expression as the exponent. We can make it negative. Let's see. Maybe I used to this estimate. So zeta, say, is R E I pi. So what is written here? Here it's written pi. R square I can write outside. Here it will be pi cosine square phi minus 2 delta cosine phi sine phi. This is this expression. So cosine is still positive. So now, if we are close to pi over 2, cosine will be close to 0, but sine will be close to 1. Delta is fixed, so if we are so this will be negative if what do we need that something like tangents beta less than pi over 2. Well, if we will make beta sufficiently close to pi. So anyway, this is less or equal than 1. On the real axis, we don't have a trouble. Our factor is less or equal than 1. Function was less or equal than 1. So this is less or equal than 1. So now we can apply Fragment-Lindelof. So by Fragment-Lindelof, this function is less or equal than 1, which means that f of absolute value of f of zeta is less or equal than e to the power minus delta imaginary part square. That's all. It's really a beautiful, typical Hardy type mathematics, beautiful and concise. For many, many years, I don't know what is the status now, but for many, many years, people tried, even 10 years ago, Tao wrote a lot about this. People tried to find proof of Hardy theorem with no use of complex analysis. I think in the end, there is a proof using Gaussian function is a fundamental solution for heat equations. So using things about heat equations, I think now such proof exists, but still it's much longer, and secretly, when you start to do PD, you're not too far from complex analysis. But formally, you can ask this question, I don't know, to second-year students after analysis course, but maybe I remember that 15 years ago, I heard a talk about this, and there were no proofs of this without complex analysis. Hardy asked me many times whether one can get rid of fragment. But this is the beauty of using complex analysis. Maybe I will make two more remarks, which will be in the homework too. One remark is that if you put a priori, if you will make bounds a little bit weaker, if you will allow polynomial growth here and here, x to the power, absolute value of x to some power and absolute value of psi to some power, then the same proof will show you that function is polynomial times Gaussian. And after Fourier transform, it will be again polynomial times Gaussian. Another thing which is a little bit more complicated, but the hint is in the homework. This I learned from Fedor Nazarov. I don't know whether it was known to Hardy or to other people. That we required two-sided bounds. We say the function decays fast and Fourier transform decays fast. It's enough to require only one-sided bounds, that in one direction function decays fast and in one direction Fourier transform decays fast. But you need to sacrifice. Theory will not be so precise. So if in one direction f decays fast with a instead of pi, in the other direction, in one direction f hat decays fast with b instead of pi, and a times b is sufficiently large numerical constant, then function is identical. Yeah, it's not difficult, and hint you will see in the second. So that's all what I wanted to tell you about Hardy's theorem, and this was another uncertainty principle. And now we will come to the next topic of our course. I still have something like 15 minutes to uniqueness pairs. We will jump something. All I told you on Monday and today is something like 100 or 90 years old, and now we will jump 50 years first. So what I will tell you now, it's already was done when I was a student. So it's not, I mean, it's not very great. Sorry, I started to erase, but if someone has a question to Hardy's theorem, to proof of the Hardy's theorem, I can stop erasing and please ask. But I really suggest very much to sit quietly to understand, to digest order of parameters when we use this twice or even 3 times fragment Lindelof in the proof. First we multiply f hat by something. This is also idea from fragment Lindelof, and then we multiply by another exponent. This idea of fragment and Lindelof is really one of the central ideas in many parts of analysis today. Not only in complex analysis, also in PD and even sometimes in OD. I used it once in dynamic consistency. But now we come to our next topic. So H will be now some space of functions on RD. Maybe we will speak about one-dimensional situation only to make our life, but we can do this for any number of variables. And for me, it will be convenient to assume that this space is invariant under the Fourier transform. But it shouldn't be Hilbert space. It could be L2, or it could be a Schwartz space, or it will be might be some version of Sobolev space, which we will talk later. If I have a pair of functions, a pair of sets, sorry, we call it a uniqueness pair. Here, in space H, if any function of H which vanishes on lambda and Fourier transform vanishes on gamma, the only function with this property is zero. Otherwise, we will say that our pair is a non-uniqueness pair. First of all, let me mention invariances in this definition. One invariance is if we multiply x by t, then on the Fourier transform, we should divide x by t. So to deal with such a pair or such a pair is the same. But we use something like this when we discussed Hardy's theory. Another uniqueness is that we can shift certainly. Shifting set lambda is the same as multiplying Fourier transform by something, so by exponents, so it doesn't change our assumptions. So what are classical examples? The first classical, let's take lambda equals c times z, and gamma is r minus half h. So here, what does it mean that gamma is a whole real line except of this interval? This means that support of the Fourier transform lies in the interval minus 1/2, 1/2. So we deal with functions from Pelley-Wiener space, which Warren discussed with you yesterday. So here, hence, we have a right to speak about point values of our function, because our function was from L2. For functions from L2, we cannot say what does it mean value of the function at some point. But here our function is analytic. So in this case, the answer is simple. If C is less or equal than 1, this is a uniqueness pair. If C is bigger than 1, this is a non-uniqueness. Why? This is a uniqueness pair. No, the simplest thing is to use sampling theorem, which you heard which we heard about yesterday. It gives an answer when C equals 1, but if C is less than 1, it's even simpler. There are many other ways to see that this is a uniqueness pair. How to see that this function is a non-uniqueness pair? Well, let's look at this function. Let's construct it by hand. Sine pi x times sine epsilon x over x over epsilon x. This is a function in L2. Its Fourier transform is a little bit bigger than what we needed for its support of Fourier transform is minus 1/2 minus epsilon over 2 pi, 1/2 plus epsilon over 2 pi. This you will check easily yourself. Function is from L2 and function vanishes. So we have small supply, so if we rescale Fourier transform so that the Fourier transform will be minus 1/2, 1/2, then function will vanish on arithmetic progression with step slightly bigger than 1. And the difference will be as small as we reach. So this is the idea, and I suggest you to work it out at home. But there are many refinements of this idea. So so if we keep gamma like this, what are other sets which are uniqueness sets? And there are famous theorems in entire function theory, which gives a kind of answer to this question, but it's by far not for this video course. But I want to present you another example, which today is also classical, and this is already was done. This is a theorem by Mikhail Benedicks. He's a Swedish mathematician. And his example, this class of function will not be, in this case, function will be from L1, so it's not symmetric. But also I will do here, it will be nice to do any number of variables. So his theorem says the following, that suppose that both functions f and f have supports of finite Lebesgue measure, then f is a 0. So function cannot be supported. So both functions and Fourier transform cannot be supported by a small set in the sense of the measure. So here we don't deal with pointwise estimates. That's why it's only measurable theorems. That's why our assumption is high. So I will start with some preliminaries. We will need a version of Poisson summation and periodization, which may be slightly different from what you heard yesterday from Warren. So I will remind you what we need. So first, periodization. stereo. So periodization is the following operation. So P, I will write formally P of x, the sum K ZD F of x plus. You can do periodization with respect to other lattices. It's not so. So x is a point in the d-dimensional torus. So, well, it depends on the taste. So torus for me, it's either interval -1/2, either this cube or this cube. With opposite faces identified. It depends on the mood where we consider convenience, whether we consider this one or that one. It doesn't matter. And important lemma / exercise, which I'm going to use, is the following: that suppose that f is L1 function, then the series converges in L1 on the torus. B integral over RT F is the same as periodization. And C, periodization is periodic function. So here I use bad notation, so I denote by hat. Here I denote by hat Fourier coefficient, and here I denote by hat Fourier transform. This is Fourier coefficient. This is Fourier transform. And this is exactly equivalent to the Poisson summation formula, but in slightly different. So I suggest you, I will use this freely, and I suggest you to check it at home. Well, now I have an alternative. So to give a proof of Benedicks theorem, I need, well, let's finish. Let's stop with this. I need 10 or 15 minutes to prove Mikhail Benedicks theorem, but I will start Friday lecture with proving of this, and then we'll move even to more content. So this theorem is already 50 years. I think exactly 50 years old. And next time we will, on Friday, we will start with this theorem, and then we will come to things which are 2-3 years old. Okay, but if you have questions, please. But you can try yourself even before Friday, because this is the main idea, and the idea we will look at the indicator function of support of f, at the indicator function of support of f hat, and we will do periodizations for both of them, and maybe one more exercise, which I want to use that if we have H is a trigonometric polynomial, this is a finite sum Just a finite sum. If H values on a set X of positive Lebesgue measure, then H. You can use, there are many ways to prove it. You can use algebraic, more algebra, or you can use that trigonometric polynomials are entire functions and use a more standard uniqueness theorem. The small obstacle here, small hurdle here is that we deal with function of several real variables. But there is a reduction to uniqueness theorem for analytic functions of unvariables. Look at many sections, one-dimensional lines. Okay, these are two facts which I'm going to use when I will prove Benedicks theorem, and I suggest you to try to. This is really simple. It doesn't differ from what Oren told you yesterday, and this is not difficult, but you need this.